to be here. Sorry for messing up the talk schedule, but our plane was delayed on...
I heard that you break the plane.
I didn't break the plane. I think they forgot how to turn it on, to be honest. But, okay, we're here now. So, yes, my talk today is about some equivariant cohomology of certain orbifolds, and this is joint work with Shintaro Kuroki and John Beck Song. The cohomology that we're interested in has integer coefficients. As we'll explain, the rational coefficients don't give you much more information from the manifold, much more different information from the manifold case. That's not quite right. It's just scrolling down.
It's because you use the word quasi-toric.
Welcome, Tony. There we go. So we begin by reviewing the well-known manifold cases so we can see the differences and similarities with the orbifold case as we progress onto that. So we start with these things that are sometimes called Toric Manifolds, which are defined as complete non-singular toric varieties, and they have attached to them some algebraic half-dimensional torus action, and they are in one-to-one correspondence with complete regular fans in Rn. And in some people call it topological version of them are these so-called quasi-toric manifolds, which are smooth 2n-dimensional manifolds with a half-dimensional compact torus action. And this torus action is said to be locally standard, such that the quotient space is can be identified with a simple polytope, and these have a similar sort of one-to-one type correspondence with characteristic pairs of this polytope and some characteristic function that labels the facets of the polytope by an integral vector, so that around each vertex of the polytope we will get an integral basis. Okay, so these well-known objects. And then, well, what is equivariant cohomology? Well, we're just going to work with these 2n-dimensional manifolds and just set this torus T to be the Tn, which is the product of n copies of S1, and we get the universal T bundle. And then if we have a T action on some manifold, we get the standard Borel vibration. And then the definition of the equivariant cohomology is the ordinary cohomology of this Borel construction, which is the total space of this vibration. Okay, so without coefficients written anywhere, we're going to be working with integral coefficients. Okay, so as is well known, the equivariant cohomology of those two families of manifolds can be written in terms of face rings or Stanley-Reisner rings of their corresponding combinatorial objects. So for a toric manifold, you can consider the face ring of its underlying fan, okay, or the Stanley-Reisner ring. And for the quasi-toric manifold, you can define the face ring of the simple polytope. Okay, so this has a generator for each facet, and if facets have an empty intersection, and then they'll disappear inside this polynomial algebra. Okay, and then if you want to find the non-equivariant cohomology rings, you can factor out by linear relations relating to the fan or the characteristic function of the quasi-toric manifold. Okay, so some properties to talk about that appear in these cases: that the torus actions are always locally standard. That's defined as in the definition of the quasi-toric manifold, and is true for the toric manifold. The quotient space, because the action is locally standard, will be a manifold with corners. Okay, so this locally looks like cone in Rn. We have isolated fixed points, and can somehow be rebuilt using a sort of global quotient construction from the combinatorial data of the manifold, and all the cohomology is generated in degree 2, so this all appears in even degrees, and we don't have torsion. So the main example is a CPN, which lies in the intersection of those two families, and we can define the fan of CPN in a sort of a standard way, and write down its equivariant and ordinary cohomology using this idea of phase rings and quotienting out by relations.
When you use that phrase, the algebraic geometers do not know that you're talking about varieties.
Yeah, okay.
There's something to remember. There's something to remember.
Okay. And then, as a wider class of manifolds that includes both of those previous two classes, we have these things called torus manifolds, which are more general and defined to be smooth-oriented closed manifolds with an effective, smooth, half-dimensional torus action whose fixed point set is non-empty. From this definition, we can immediately imply that all our fixed points are isolated. There are combinatorial objects, a bit like fans, associated to torus manifolds called multifans, coming from the work of Hattori and Masuda, although they don't really enter into our results that we'll discuss in this talk here. So if the T action, the torus action on the torus manifold is locally standard, then we'll also get the quotient space being a manifold with corners. Okay, it's going to be important. Right. So instead of associating a combinatorial object like a multifan to a torus manifold, we're going to associate a combinatorial object called a torus graph to a torus manifold. So starting with a torus manifold, we can consider one of the isolated fixed points. And then taking the tangent space at that fixed point, we can think of that as a representation. There's an action of a bundle over a point, so it's a representation, a complex representation. We can split it up as a sum of irreducible complex torus representations, which are all one-dimensional because the torus is abelian. Okay, so we can think of these as maps, homomorphisms from the torus to S1, and taking the character of such a map gives you an identification with an integral vector. And now what we're going to consider is the set of all two-dimensional submanifolds of the original torus manifold M, each of which is fixed pointwise by a codimension 1 subtorus. Okay? And each of these will be diffeomorphic to a copy of CP1 or to a two-sphere, which will contain exactly two fixed points. Okay? So the picture that we have is we've got our manifold with its fixed points, and then these copies of CP1 linking these fixed points, these spheres. So it looks like a link of sausages or something like that. So we can then define an n-valent graph from these objects, where the vertex set of the graph is all the fixed points of the manifolds, and the edges are these copies of CP1, or these two spheres relating each of the vertices. Okay, so it's n-valent, and we label each of the oriented edges with its sort of corresponding weight coming from the decomposition of the tangent space as the sum of n complex one-dimensional representations. Okay, so we're getting an n-valent graph with its edges labeled by irreducible representations of the torus. Okay, so one example, which is not a toric manifold or quasi-toric manifold, is the example of an even dimensional sphere. Okay, so this is a torus manifold with a torus action, where you get by suspending the standard coordinate-wise torus action on an odd dimensional sphere. And so we get a graph with two vertices, exactly two vertices, and n edges between them. So we can label these by the standard basis vectors of Zn. So this is a torus manifold that's, as I said, not toric or quasi-toric for n larger than 1. Now, Gwilliam and Zara, after GKM, did this, decided going to abstract the notion of torus graph. So you just take your abstract graph, so abstract n-valent graph with its set of vertices, its set of oriented edges, so each edges appear twice in the set E gamma. And we have, the I of E is the sort of the initial vertex of this oriented edge E, going from I of E to T of E, the terminal vertex of the edge E. And then for every vertex of the graph, we define this set E gamma P of all the edges emanating out of some vertex P. Okay, so all the edges emanating out of I of E would be all the n edges coming out of I of E. And then we define what's called an axial function, which is a map from the set of oriented edges to the irreducible complex representations of the torus that satisfy the three conditions. Okay, so the first is just you get the plus or minus sign if you change the orientation of the edge. Around each vertex, the labels on the edges form a basis of the integers. And then the third condition gives you a relationship between the labels coming out of one vertex and the labels coming out of another vertex that are joined by an edge. And they're essentially the same modulo the labeling on the edge. Okay, so a torus graph is a pair of this graph with an axial function. And to each torus manifold, we can obtain a torus graph, an abstract torus graph. Okay, but we can also study these torus graphs as abstract combinatorial objects in their own right. Okay, so as most of you know, this condition that the odd degree cohomology of some of these manifolds vanishing is very strong. It's a very strong condition. We know for the torus manifolds that if the odd degree cohomology of the manifold does vanish, then this will imply that the action is locally standard, and so our quotient space will therefore be a manifold with corners. We can also get this if and only if condition where the odd degree cohomology vanishes if and only if the action is locally standard, and that the quotient space, which we know is a manifold with corners, is also face acyclic. So each of the faces is cyclic, and so is Q itself. And this will imply that we can reconstruct the manifold from this combinatorial face acyclic manifold with corners Q and the torus by the standard global construction. Okay? So from all of this, we can see how strong this condition that H, the odd degree cohomology vanishing is, that we can write it as an H star BT module, which is a free, we can write the equivariant cohomology as a free H star BT module. It implies the Serre spectral sequence of that vibration that we saw earlier collapses. And then if we consider the inclusion of the fixed point set into the manifold, we then will get this injective map I star from the equivariant cohomology of M into the equivariant cohomology of the fixed point set, which we can then write as a sum of copies of H star BT, one for every fixed point in the manifold. Okay, so the goal to describing the equivariant cohomology of the manifold is to describe the image of this map I star. Okay, so now we go back to this abstract notion of an abstract graph and define something called the graph cohomology, which is also known as piecewise polynomials on the graph. Okay, so for each vertex, we are attaching to it a polynomial, so an element of H star bt, which we know is a polynomial algebra, with n generators of degree 2. And we have the condition that if two vertices are connected by an edge, that the polynomials attached to those two vertices agree modulo the labeling on the edge. Okay, so somehow they agree piecewise. So it's a sort of a theorem that sort of began with GKM with real coefficients and was improved by Masuda and Panov, that we find that if the odd degree cohomology of a torus manifold vanishes, then the equivariant cohomology of the manifold is exactly the equivariant cohomology of the graph. So we sort of reduce it to a combinatorial setting. Okay, and the sketch of the proof, which we'll quickly see here, as it doesn't really, this part doesn't really change for the orbifold case, begins with the fact that the observation that all the isotropy subgroups are connected, so this Chang-Schgelbred sequence will be exact with the integer, with its integer coefficients. Okay, so there's our map. Oh, there's our map I star from before, where now we've sort of, for some reason, changed notation, where now M0 denotes the set of fixed points, and M1 is the set of one-dimensional orbits, so they correspond to the edges of the graph. Okay, so we can now identify the equivariant cohomology with a kernel of this map delta, as it will be the same as the image of that map I star, and then we can rewrite this map delta in such a way where on the right hand side we're taking copies of H star bt E, which is now an n-1 dimensional torus associated to the edge E, so you can consider the kernel of this, the image of the axial function associated to E. So remember, that's an element of, it's a homomorphism from T to S1, so its kernel would be an n-1 dimensional torus. And this is defined exactly how we would want it to be defined, so that the difference of the two labelings restricted to H star bt will vanish. Okay, so this kernel of delta is exactly the image of the I star. We can describe it exactly as piecewise polynomials that agree up to some labeling. Okay, so that gives us a way of, it just really changes the setting from the equivariant cohomology of the manifolds and geometrical setting to some combinatorial setting. But we still haven't really calculated anything as such. And this changes when we take some specific elements of those, some specific piecewise polynomials in that graph cohomology. And these are called the Tom classes of faces of the graph. So if you take a k-dimensional face of our torus graph gamma, so you can think of that as some sort of sub k-valent graph in this n-valent graph gamma that's preserved under the axial function alpha, we define what's called the Tom class associated to that face. Okay, so that's going to be one of these piecewise polynomials, so we're mapping certain polynomials to the vertices of gamma, and they will be 0 if the vertex is not inside the face F. If it is inside F, we will take a product of the labels coming out of emanating from P that are not inside F. Okay, so hopefully we'll see an example of this later. And so, as a lemma, each Tom class of a face of the graph is a piecewise polynomial of the graph. Okay, and then we also get this standard relation coming from the combinatorics of the graph, where the wedge stands for the minimal face that's containing the face G and the face H, and this E is a connected component of the intersection. So Masuda and Panov then give generators and relations for these graph cohomologies, or these piecewise polynomials, where we have a generator associated to each face, the generator being the Tom class of the face, and then we quotient out by the ideal coming from this relation. Okay, so that's the manifold case. And now we move on to our work, which is to do with orbifolds. And like before, we have the similar setting, those two families to begin with. So an orbifold, for those who may not be familiar, is like a manifold, except it locally looks like the quotient of Euclidean space by some finite group action. Okay. So we can think of toric orbifolds as complete simplicial toric varieties. So the difference now is we've got simplicial instead of smooth, and again this comes with a half-dimensional torus action, and it's associated in one-to-one correspondence with complete simplicial fans. Okay, so this is where I'll talk about quasi-toric orbifolds, and you can define these similarly to quasi-toric manifolds, where you have a two-dimensional orbifold with a half-dimensional torus action, where the action is locally standard and the quotient is identified with a simple polytope, and that's in one-to-one correspondence with characteristic pairs with, again, a simple polytope, but now the characteristic function will not necessarily give you a basis around each vertex, but just a linearly independent set of n integral vectors. So linearly independent in the Z setting, in the integral setting. Okay, and a similar thing is happening with your fans for your toric orbifolds. Okay, and so the main example, the sort of generalization of the complex projector space example that we saw before, is something called weighted projector space, which again lies in the intersection of those two families. And you begin by giving some weight vector, n+1 natural numbers, and you define the weighted projector space in an analogous way to complex projector spaces, somehow defined by taking an odd-dimensional sphere and quotienting out by S1, by an S1 action, but this S1 action now acts in some weighted sense that's associated to this weight vector chi up here. So CPN will come by just taking all your weights as the number 1. Okay. So these are weighted projector spaces. These are quasi-toric orbifolds over a simplex. Okay, and Kawasaki proved quite surprisingly that integrally these or additively they're isomorphic to CPN. We just get a copy of Z in every even dimension there's no torsion, but the product structure is somehow twisted. So these these gammas are the generators in these groups, but there's some twisting, and these These L's are just some numbers, they're integers coming from the weights. So the difference between the orbifold case only really comes looking integrally, because we see that rationally for toric orbifolds and quasi-toric orbifolds, actually we get the same integral cohomology as we would if we took a rational picture for manifolds. So we just get phase rings. Okay, so in some sense we've not captured the subtleties of what's going on in the orbifold setting here. So it's only when we go to integers that we start to sort of capture the difference, a bit like in the case for the cohomology of weighted projective space. Okay, so now we extend again torus manifolds to torus orbifolds. So we're looking at even-dimensional, smooth-oriented closed orbifolds with effective action whose fixed point set is non-empty. And we define what, in these slides, are called a rational axial function associated to such a torus orbifold. So it looks much the same as before, except now we're labeling each edge by a vector that has rational elements and satisfies similar conditions. So the second condition is that, okay, around each vertex we're going to get something linearly independent, not necessarily, well, okay. And then the first condition, remember before we just had that the alpha of E was plus or minus alpha E bar. So if you change the orientation, you just possibly changed the sign. But now we're also asking for the existence of these numbers which soup it up to an integral statement. So you just multiply up until your rational vector becomes an integral vector. And then lastly we get the same sort of condition on the relationship between labels coming out of vertices attached by an edge, except we've souped it up using these integers associated to each edge. Okay. So given such an object, a rational torus graph, we can define certain cohomologies. The first is sort of the integral one, where we're attaching to each vertex a polynomial with an integral polynomial, so that it's very much the same as before, except now we have to soup up this label to an integral label. So we just multiply by a certain RE. And we'll be using some sort of rational version, which looks exactly the same, except now we're mapping into polynomials with rational coefficients, and we no longer have to care about whether we're modding out by something rational or not.
Just show me what was RE again?
RE. So RE is an integer, positive integer, usually, associated to each edge, so that RE, alpha E, will be an element in Z, so it'll be an integral vector. So you can just.
So RE is unique for each E.
If we ask that it's positive and minimal, then it will be unique. Yeah. For some cases, you don't care whether it's you just need something that's good enough. Okay, but actually,
in the definition of graph cohomology, you use RE.
Yeah. So there we will assume. Yeah. Let's assume that it's unique. So let's assume it's positive and it's minimal. So therefore, it's unique. Okay, associated to each edge E. Yeah. So. Okay, so there's a difference between sort of the integral and the rational. Okay, so then our first result is that if we take a torus orbifold that has its odd degree cohomology vanishing, as in the manifold case, we can show that the equivariant cohomology of the torus orbifold coincides with the equivariant cohomology of the graph. And this is all with integer coefficients. So this is this integral cohomology of the graph, and the integral cohomology of the torus orbifold as H star BT algebras. And the proof of that is much the same, it really follows very similarly to the proof of the manifold case. I guess the hardest part is actually working out the right definition for the graph cohomology to then be able to write this down. So now we're going to go and try and find what are the generators and the relations, what is the analogues of the Tom classes for the orbifolds. And this takes obviously lots of inspiration for how it was done in the manifold case. We first define this ring of start with rational coefficients, and we have a generator for each face of the graph. Okay, and we map each of these generator to the Tom class of that face. And now this is in rational cohomology. So this is defined exactly as it was beforehand for the manifold case. The same definition. You just take your graph and you just consider the edges emanating out of your face, and you label the vertices with the corresponding polynomials accordingly. Okay. So this would give you something rationally, but you'd lose a lot of information. So to keep track of the information, we define a certain subring. So inside this polynomial ring, we have the subring of the polynomial ring with integral coefficients. And then this strange notation, Z gamma, is going to be a subring of that ring. So I've just spotted this mistake. This should actually be, I think this Q should be a Z. But this is a set of polynomials, so that when we map them across, each vertex will be integral, will be an element of H star BTZ. It'll be a piecewise polynomial, an integral piecewise polynomial. So some sort of integrality condition. So this, because this set is closed, this will form a subring. Okay, and then we show that the equivariant graph cohomology with integer coefficients is exactly the quotient of this ring by a similar set of by an ideal generated by a similar set of relations. Okay, so under this map, this relation will just go to 0. Okay, so we've given, with the condition that the odd degree of cohomology vanishes, that the equivariant cohomology of the torus orbifold can be written out in terms of generators and relations, those Tom classes, and similar relations to the manifold case. And if we like, we can also calculate the non-equivariant cohomology by generating out by certain linear relations coming from the combinatorial data as is well known beforehand. So we've seen beforehand a paper of Tony, Soman and John Beck.
That first guy there.
No? Oh. Some people don't have. Some people have conflicting ideas about them as well.
Yes, spelling.
Oh.
This is Lebanese spelling.
Oh. Apologies for the
For
misspelling.
weighted projective spaces,
Yes.
this was known.
This is definitely known. Sorry. Yes.
What about the integral case is about 1,000 years old? What about the integral? So for weighted projective spaces, the integral equivariant cohomology is computed.
The integral. Well, yes, by you and Nige. Yes, for weighted projective space. Maybe I should have made that more clear. For weighted projective space, this was done, I wouldn't say thousands of years ago. Certainly in your lifetime. But
Low marks, low marks.
yes, for weighted projective spaces, this was done quite a while ago, and extended by Tony, Sherman, and John Beck to more sort of projective toric orbifolds, which I guess we've now done to sort of all sort of these torus orbifolds under this very, very strong condition that this odd degree cohomology vanishes.
It's a nice, clean result. The GKM result is very nice and clean.
Thanks, yeah, I mean, it can get messy if you try to do a calculation. Okay, so I think let's finish on time because I was so late. I was going to run through a little example, but maybe it's time for dinner, so I'll finish there.